Hello. So today we are going to take a look at this problem called sort the matrix diagonally. And the problem says we get an m by n matrix and we want to sort it in ascending order from top to left, from the top left to the bottom right. What this means essentially is if we get a matrix like this, we want to sort all the diagonals in the matrix and return a result. So for example, this is the first diagonal, 19, that's already sorted. Then we get 10, 17, that's already sorted as well. Then 8, 11, 0, so we sort that. To sort it, we get 0, 8, 11, so 0, 8, 11. And then 12, 1, to sort that, we get 1, 12. And then 13 is already sorted, and so we got that. So essentially, it's just take the matrix, sort each diagonal as in ascending order. And that's pretty much it. So let's see how we can solve this problem. Okay, so how can we solve this problem? I wrote down here the matrix example we had and just surrounded the diagonals here. So we have the diagonal just 19, diagonal 10, 17, this diagonal 8, 11, 0, diagonal 12, 1, and 13. So let's try to make an observation about these diagonals here. So the coordinates of the first diagonal is just 2, 0, and the difference between I and j for these coordinate is 2 minus 0, which is 2. For the second diagonal, we have 1, 0, which is 10, and then we have 2, 1, which is 17. And if you can see, I minus j here, which is 1 minus 0, is 1, and 2 minus 1 is 1. So the difference is the same. You can notice for each of them. Here, for the third diagonal, 8, 11, 0, the first coordinates, the first element coordinate is 0, 0, the second coordinates are 1, 1, this last one is 2, 2. And you can see the difference between, again, I and j is 0, so it's the same for all of them. The same for the other diagonals, 0, 1, and 1, 2, the difference is minus 1, the same again. And this is like a property, or well-known property of the matrix diagonal, is that each diagonal, the difference between the row index and the column index is always the same for the same diagonal. And so from that property, what can we do? So let's just write that down here. So for each diagonal, the difference between row index and column index is the same. For each cell. So this is the main observation that we'll go from here. So to do this, we will start off with, so what this means is that, well, we could just have a map that maps from this difference that defines each diagonal to the values in the diagonal, right? Why would that be useful? Because if we do that, we can sort each diagonal, and then we need to reconstruct the matrix again. So the first step we can do to solve this here is just create a map with keys being this difference here that defines the diagonal, and the values will be just list of values in that diagonal. So what this would mean in our case here is that, well, for the first diagonal, which has 2, so let's just write this down. So for 2, this one where the difference is 2 here, we have just 19. For 1, the values are 10 and 17. For 0, the values are 8, 11, and 0. And for minus 1, the values are 12 and 1. And for the last one, which is minus 2, the values are just 13. Right? Okay, so now we have the map that we created from step 2. Our second step would be to sort them. Right? So sort each diagonal. because that's what we are looking for. We could definitely sort them like in ascending order, right? Get 19, 10, 17, since that's what the problem asks us to do. But the problem with that is if we try to reconstruct them, we would have to start with this one, position 0, position 1, position, and then position 2. So that's not very helpful, right? Because what we want is, because getting the index, we would have to, it would be complicated. We would have to keep track of I and j. So what we can do instead is sort them in the reverse order and use pop, because pop will allow us to get, if it's sorted, if they are sorted in reverse order. Let's say if we have 3, 2, 1, right? Then pop will give us 1 first and removes it. And so if we do pop again, we'll get 2. So that makes it easier to reconstruct. And so what we do here is sort each diagonal in reverse order. It will be clear why that is helpful even more once we do it. And so here, what this would mean is we would have 2 with just 19, 1 would be 17, 10, and then 0 would be 11, 8, 0, minus 1 would be 12, 1, and then minus 2 would be just 13. Now the third step, now we have the diagonals in the map sorted. The third step would be to reconstruct the map, the matrix, so that the diagonals are sorted. The matrix using sorted diagonals. So how can we do that? Well, we could just do very simple here. So we could just start with 4. Let's say rows is just the number of rows we have. So we'll go through all the indices of the rows. And then what value should go into matrix of R and C, right? So for this one, well, if we just take 19, we could just pop 19. For the second one, it's 10 should be here and 17 should be here. And so since we are going in sorted order, the first element that we get should be the smallest one. So we should just pop. So if we pop, we can get 10. And the same thing here, the first element should be that we get, since this is in sorted order of indices, should be the smallest one. And so if we do pop, we will get this one, and then it's removed. If we do pop again, we'll get this one. And so we could just here say diagonals. What should be the key? The key should be the same key that we used initially, which is the difference, so that we can get the right spot, the right bucket here. And so to do that, we are just going to take the same that we take when we reconstruct here, which is just taking the row minus the column. We will do that here and do pop to get the smallest element. And that's pretty much it. And once we do that, we have the matrix sorted in the right order. Okay, so now let's write the step that we just did in like an algorithm, like the full solution, right? So the function would be sort matrix diagonally, right? So we'll get the matrix. Now the first step would be is to create the map that we will use in step 1 here. So we need to create the map, and so let's call that diagonals. So we could just use a collection such that each value is a list, right? So that would be default dict for the list here. And then we will need to construct the matrix and construct the map. And constructing the map is just going through the row and column, taking the difference as the key and adding whatever value to the bucket that it belongs to. So we will be traversing row by row, and then for each row we'll go through each column and take, for example, 8 and say, okay, 8 is 0 minus 0. It belongs to the bucket 0, so we'll add the element to it. Go to 12. 12 has indices 0, 1, so it belongs to bucket 0 minus 1. So it belongs to bucket minus 1. So we'll go here and put 12. And we'll keep doing this as we go. And so to do that here, we'll just go through the rows So we'll need to first put the number of rows in rows and the number of columns in columns. So the number of rows is just the length of the matrix, and the number of columns is just the length of the first row, right? I'm assuming here that the matrix contains at least one element. If we don't want to assume that, we can just do a check for empty before doing the rest of the solution. Okay, so now we will say for R in rows, in the range of rows, right, to get the indices of the rows, and then for C to get the indices of the column in range of column, right? The next step would be to add the element that we are traversing to in the bucket that it belongs to. And so to do that, we have the diagonals map. We are going to take the key, which is R minus C, and since by default it's a list, so even before adding any element, by default it will return as an empty list. So we don't need to create it. So we can just do append. So if there is no element, it's an empty list. If there are elements, this value will be added to them. And so what is the value? The value is just matrix at these indices, right? And now once we've done this, this is step 1 here, constructing the map of the diagonal. Next we will do step 2, which is sorting the diagonals. Of course in reverse order so that we can use pop. And so to do that, we will just go through each diagonal in the diagonals values and sort them in the reverse order, sort them in place, right? And so to do that, we'll just do diagonal dot sort, and we want to sort it in the reverse order, so we can just in Python pass reverse equal to true. And now we have the diagonal sorted, we can do the third step, which is reconstruct the matrix using the code that we already wrote here, using pop because we sorted in reverse order, so pop will give us the smallest element. And so to do that here, we could do the same loop almost, so in range of rows. And for column index in range of columns. Now we can just say the element at position RC is just the smallest element in that bucket of the diagonal. So that would be diagonals. The bucket is R minus C, and we could just pop the element. And that's pretty much it. We can at the end return the matrix that we just reconstructed. So this is step 3, which is reconstructing the matrix. Right? Now, so that's pretty much it. The first solution, construct the map, sort them in reverse order so we can use pop, and then get the matrix populated in sorted order. And that's pretty much it. Now, if we look at this in terms of time, while we are doing here, this step here, here we are doing O of M. So if M is the number of rows and N is the number of columns, we are doing M by N, right? Here we are doing sorting, right? So it's O of N log N, right? But N is the length of the diagonals here, and so diagonals are at most, so the number of values in a diagonal that's at most it's going to be O of the minimum of the number of rows and the number of columns, right? Because if we have a lot of rows, the diagonals won't be, the number of values in the diagonal would be at most the minimum, right? And so what this would mean here is the sort, remember, is over log n, such that n is the length of the data or the array we are sorting. And since the length of the array we are sorting is this, let's just give this here min d. So let's suppose d is equal to the min, which is the length of the diagonal. So what this would mean is that this here would be O of d log d, right? Which is O of min of mn n multiplied by the log of mn, of the min. Sorry, this is getting long, but which is why we should just make it shorter using this, right? And then the loop here is also O of m by n. So if you take all of these together, our time complexity is it's O of m by n 2 times, right? Plus d log d. So what we can say here, so the diagonals values, the overall values, are actually mn. Those are the number of values in there, right? So we can say that here this is just O of m n log d time. And then in terms of space, so let's write this down, O of m n log d time. And in terms of space here, we are using this map here that contains at most all the values in the array, right? So all the values in the matrix, so that's O of mn. And that's pretty much all the space we are using, since we are using the map here. So this is space we are using. And yeah, so that's it here. Let's just write this down, run it on some examples, and that's pretty much it. Okay, so let's see if so I have here just the code that we just went through in the overview, and it's just we have the map of the diagonals, and then we fill it up by making the keys be the difference between the row index and the column index. And then we sort the diagonals in the reverse order, of course, so that we can do pop here to get the smallest element first. And then we populate the matrix again by picking from each diagonal the value. So the bucket that the elements belong to is R minus C. And we pop the smallest element, that way we can get them in sorted order. And that's pretty much it. And then I have here some examples that we can test with, but it should work on any matrix that has length at least 1. And so if we run this, test pass. If we want to handle empty matrices, we can just do a special case at the start. And yeah, so that's it pretty much for this problem. Thanks for watching, and see you on the next one. Bye.